Hi, it's great to be here. There's some fantastic talks in this session. Probably not going to answer this question by the end of the talk, but let's see. I'll keep you in suspense until halfway through. This is a figure from a paper that Rory Barnes and I wrote a few years ago now, where we looked at the fact that M-dwarfs take a really long time to contract fully during the pre-main sequence phase, and how that can negatively affect planets in the habitable zone because they experience actual total fluxes much larger than the runaway greenhouse limit for up to hundreds of millions of years, especially around low-mass M-dwarfs such as Proxima Centauri. And so what that means is that you're in a runaway greenhouse, assuming you have an ocean of water on your surface. You're in a runaway greenhouse for several hundred million years, during which time water can escape to space and oxygen can build up. The heavier oxygen atoms are preferentially held back in the atmosphere. And so this is a figure from our paper where we show the amount of water lost in terrestrial oceans as a function of stellar mass and solar masses and position in the habitable zone. So this is the recent Venus, early Mars limits, and then the more conservative habitable zone bounded by these white lines. And so you can see that for a planet such as Proxima b, roughly in this position, in the relative position in the habitable zone, around a star about 1.12 solar masses, you'd expect it to lose lots of oceans based on this mechanism. And you might also expect it to build up something like on the order of 1,000 bars of oxygen in its atmosphere. And obviously not all of that stays in the atmosphere. It can get reacted away with other components in the atmosphere or reacted away at the surface since oxygen is so reactive. But we can do better than this. Obviously, this is a figure for a 5 Earth mass planet, and these escape rates change a lot, and it also depends on the details of the X-ray flux of the star. So we can do a little better than this. And what I'm showing here is essentially the framework for what we call VPlanet, which is Rory Barnes' planet evolution simulator, whose ultimate goal is to try to address whether or not any given planet might be habitable by coupling processes ranging from thermal evolution of the planet's core to atmospheric escape to stellar evolution and even galactic evolution, as we'll hear from a few talks later today. And so for the specific case of atmospheric escape and how it affects the water content of the planet, what we have as input are basic properties of the planet, such as its mass, radius, semi-major axis, some initial properties. So as Tony hinted earlier, the amount of hydrogen that the planet forms might matter because hydrogen will escape first because its scale height is much larger. That's what's going to drive the hydrodynamic wind early on. And so if you have a substantial amount of hydrogen, that could actually protect your volatile content closer to the surface. Obviously, you need to input what you believe the initial water content of the planet to be when it formed. And then you put everything into this little black box called VPlanet with some parametrization for the evolution of the luminosity of the star, the evolution of the X-ray and extreme ultraviolet luminosity of the star. You model the escape efficiency with a hydrodynamic parametrization and some details about where you put the oxygen that's being formed. You crunch all the numbers, and you get your answer, and you ultimately answer whether the planet is habitable or not. So let's do that. The planet, as we saw, the minimum mass is 1.27 Earth masses. Its radius is 1.07. Bear with me. The semi-major axis from the Discovery paper is 0.049. You can look at some population synthesis models and come up with some plausible amount of hydrogen that it formed with, some plausible amount of water that it formed with. You can look at some stellar evolution tracks for the observed metallicity of the star and the observed mass and some mixing length parameter that you hand wave. And same thing for the XUV luminosity. We observe it following a power law based on this study and several others. You can run a hydrodynamic code to get the escape efficiency, which is the fraction of energy of the incoming XUV energy that's converted to escape. And some parameterization for the oxygen absorption, such as Laura Schaefer did for GJ1132b, where we're still working on this, but where we actually calculate the rate at which oxygen is absorbed into the magma ocean on the surface. And so you put this all into VPlanet, and you get the answer that, in this specific case, you get 60 bars of oxygen remaining in the atmosphere, no hydrogen, no water. The planet is not habitable. Thank you. I'm just kidding. I'm just kidding. This is a terrible way to answer this question. This is not my conclusion slides. And now I will reveal to you that I'm not actually going to answer this question because we don't yet have enough information. So the point of this talk, I was actually a little scared when I saw Alex Bixel's talk. It was like, he's giving my talk. But the point of my talk is to just convince you that Bayesian statistics is what we need to do to answer these kinds of questions. We need to be very rigorous, very robust about treating uncertainties, making sure that we're accounting for all prior information so that we can actually get a robust answer to the question. Pointing to a planet and saying it's habitable or it's not habitable, we're not there yet. We're not going to be there for a very long time. We're going to be able to hopefully assign probabilities with very large error bars. And so let's walk through that. We can't really say any of these things with that much confidence. In fact, there are error bars associated with all of these numbers and buried in all of these models, right? Each one of these models here assumes several other parameters. And if you just go to a study and like get their maximum likelihood estimate for what, I don't know, the hydrodynamic escape efficiency is for a certain planet, you are sweeping under the rug a lot of uncertainty. So you need to propagate it along in your models correctly. And so the first takeaway is that uncertainties matter. And so we saw several talks earlier that you can't just say that Proxima has 1.27 Earth masses. That is the minimum mass. Geometrically, it could have a much larger mass and be on a larger inclination. And there's also an uncertainty on the minimum mass itself from the noise in the RV data. And so you actually get a distribution like you saw from a couple talks earlier, where, it's the probable mass is close to that, but this is really a distribution. Same for the semi-major axis, right? What you get from RV is the period. There's a large uncertainty. To convert that to a semi-major axis, you need to account for the mass of the star, which there's a large uncertainty there. And so you get a distribution there as well. So uncertainties matter. Data matters. I can't just use a luminosity evolution track to compute the luminosity of the star if it doesn't match the present-day luminosity. And so you need a robust way of accounting for that. Now, M-dwarf isochrones are notoriously bad because, as Suzanne Hawley always says, there does not exist a typical M-dwarf. All M-dwarfs are different. They're not all going to follow the same track. There's a very large spread, especially at low M-dwarf masses. And so you need to somehow account for, the best handle you have on this is the observed data, right, which is the luminosity of the star today. And then you can use the track to backtrack what it was in the past, conditioned on the fact that you know what it is today. And the same for the XUV luminosity. And then finally, and this is the most important one, priors matter, right? I can't just assume a certain initial volatile inventory. I need to look at population synthesis models. And so we need to do things like look at formation rates and how quickly planets accumulate gas from the disk in order to get initial hydrogen fraction, which matters a lot for the amount of water that finally escapes from the planet. And the same for oceans. So we need to figure out, this is, as you'll see, this is the principal thing that we need to figure out is how many oceans these planets are forming with. Because I cannot tell you whether this planet is habitable today or not if we don't know how much it formed with. And so priors matter. And so we need to move away, especially if we're going to try to figure out whether planets are habitable, we need to move away from this maximum likelihood approach and take a more Bayesian approach, where we transform these priors, these data, these uncertainties, into a posterior distribution for how much water there is on this planet today. And the way we do that, so this is work in preparation, is we have some input vector where we have all our priors and our data, the mass of the star, some parametrization of the XUV saturation time and the power law that describes the XUV evolution, some properties of the planet and the initial volatile content. You have your model outputs, right? You feed this into VPlanet and you get this out, the luminosity of the star today, the XUV luminosity of the star today, and more importantly, the amount of water today. And the way you treat this in a Bayesian sense is you assign some likelihood function, right? You want your model output to match the present-day stellar luminosity, and the same with the XUV luminosity. You want to fold in all your prior information there. And there's no analytic way to convert this into a posterior distribution for water, so you need to run something like a Markov chain Monte Carlo simulation, where you use this likelihood and run a long chain of simulations to get an actual posterior. And so we started doing this. What I'm presenting here is very preliminary results. But these are posterior samples, as an example, for the stellar evolution. And so the red line is the mean of all our samples. And each of the black lines are just randomly drawn from our MCMC posteriors. This dashed line is the observed value for each of these quantities, the stellar luminosity, XUV luminosity, and stellar radius. And you can see that on average, they match the present day value, but there is a very large spread after you account for all your uncertainties. And at the end of the day, you might get something like this. And again, there's a big asterisk here. This has not been marginalized over population synthesis outputs. I have not robustly accounted for oxygen sinks. And so this is just an example. But at the end of the day, you'll get something like this, a marginalized posterior distribution for the water content today with a large peak close to 0, but a long tail. And these are very non-Gaussian, right? I can't quote this as 2 plus or minus 3. It's a complicated distribution. And the same for oxygen. And we can start to see that, as Tony was saying, like in a lot of cases, no matter what you assume, the planet does lose a lot of water. But there is a broad and non-negligible tail where the planet maintains oceans today. And another thing that's interesting, I know I'm running out of time here, so I'll do this quickly. Another thing that's interesting is to look at correlations between parameters, which is what MCMC allows you to do. And you can see that oxygen and water are very tightly correlated. The more water you lose, the more oxygen you build up. But this correlation eventually breaks down because oxygen escape, or water escape, is self-limiting. Once you start building up a lot of oxygen, the hydrogen needs to diffuse up through the oxygen, and it throttles the escape rate. And so that correlation breaks down. You can look at these joint posteriors for all your parameters in your model, and you can stare at this for a couple hours and put this on a T-shirt. I think it's really pretty. But maybe I'll do that. The strongest correlations here, and this is my last point, obviously the water and oxygen, but also the saturation fraction, the XUV saturation fraction, and the amount of water that builds up. Now, the XUV saturation fraction is the ratio of the stellar XUV luminosity to the stellar bolometric luminosity early on when the star is young. And for M dwarfs, that is somewhere around 10 to the minus 3. So 10 to the minus 3 of the star's light is emitted in the XUV early on because it's very active. But it's not very well constrained. There's a very large spread. And we can see that our model is extremely sensitive to that. The higher that value, the more water you lose. And so until we actually pinpoint that exact value for Proxima Centauri, which may or may not be possible, we're not going to be completely sure about our answers. And we're going to get a large distribution for the water content. So as I said before, I did not answer the question. I never intended to. Because this is an incremental iterative problem that we're going to have to do this iteratively, right? Like right now, we have certain data, certain prior, certain uncertainties. We can come up with these large, long-tailed probability distributions for water, but they're going to get narrower as data comes in, and hopefully that'll be soon. And so we can certainly look at this with a glass half full attitude, which absolutely we should, because this is the closest potentially habitable planet, and we should be excited about it. So I'll leave it at that. I'll take questions. Thank you.
Thank you, Rodrigo. We have time for about 1 or 2 questions, so please.
Thanks. Sorry. Very nice talk.
Thanks.
Evgenia Shkolnik, ASU. So of all the observables, what is the most important one that you need to know? Did I hear XUV?
Yeah, you heard XUV.
That was my question before you said it.
Yep.
Okay, so in that case, I will advertise for Adam Schneider's talk this afternoon that we'll be able to answer that for you for the Proxima b spectral type.
Awesome. Thank you. I look forward to it.
Great job. I think this is definitely the right approach. So here's the mean question. How do you account for missing model physics? There's all sorts of physics we're not accounting for. It's a 1D model.
Yeah,
You just chose 2 compositions, water and hydrogen. So how do you, to channel the inner Fortney here, how do you channel the unknown unknowns?
The short answer, I have no idea. Right, we're trying to answer a very difficult question. Ultimately, it's not about how much water is on there, but is this planet habitable and is it inhabited? And there's tons of physics there we don't understand too. And so I think this is a start, but absolutely, this is going to depend a lot on further modeling, further atmospheric modeling to actually map out all the possibilities so that we can properly account for them. This is just what we currently know, and we're going to have to build on that.
All right, unfortunately, we're going to have to move on, so I'm sorry for that, but you can talk to Rodrigo hopefully after the talk. So let's thank him again.